Okay, so for the last topic in this lesson on statistics and correlation, we're going to discuss the idea of multivariate analysis. Now, this applies in situations where your system is described by a large number of variables and you want to reduce them to a manageable number. You want to reduce the dimensionality of the system. And that's because you think that some of the variables are strongly correlated, so they tend to vary together, so that if one changes, the other changes, so that you don't really need both variables. If one changes, then you know what the other one is going to be. And to illustrate that, I've taken this example where we can imagine we've done a survey of people about their TV watching preferences. So there's a range of TV programs here, and these are different people, A, B, C, D, E, and we've ticked off which programs they like. And what we might notice when we do that is that these programs actually fall into a number of different categories. So we've got sports programs, for example, and we've got comedy programs, The Office, Only Fools and Horses, and we've got sort of history or history type documentary programs. And we might find that if people like watching Match of the Day, then they also like watching Question of Sport and Sky Sports News. And so, that applies to this person. And okay, they might be slightly different, that they also like this particular history program. But by and large, if they like the sports programs, they like all the sports programs. And same for this person here. Whereas a person who likes comedy tends to like all the comedy programs. So rather than regarding each person as a completely unique individual described by these 9 different programs, we can reduce them into 3 basic categories, or we might find that that's the case. So they basically fall into the sports fans, the comedy aficionados, and the history buffs. And so instead of having just 9 different programs to describe people's preferences, we can just describe them in that one variable that those 3 variables and where they fit on those, because some people might combine being a sports fan with a bit of a history buff, for example, but it's those 3 variables, sports, comedy and history, that are the underlying factors. Now, in that situation, I've described it that we sort of already got an idea of what our factors are, that we've got these sports, comedy and history programs, and we're trying to look at, how do people vary in terms of those key underlying factors. But it might be that we don't actually know that, how these programs are divided up. We want that to come out of the analysis. So we don't make any preconceived assumptions that certain ones are sports programs, certain ones are comedies, and that people are likely to like particular categories together. We actually just look at our data and see what comes out of it. So we might see here that here's a person who likes Match of the Day, and they also like Question of Sport, and they also like Sky Sports News. And here's another person who likes Match of the Day, and they also like Question of Sport and Sky Sports News. And we might find that that's pretty much the case for everybody, that if they like this, then they like those. So we haven't assumed in advance that these are sports programs, but what we have noticed is that people who like one thing like all the others. And then we can say, well, those programs go together, and we can be agnostic about why it is. We may then investigate, but it's just come out of the analysis. We haven't assumed anything about the our variables, the programs in this case, in advance. And those describe 2 types of multivariate analysis, which is what I'm going to look at. So the first one is, well, we'll start with principal component analysis, which applies in the situation where we don't make any prior assumptions about what the underlying factors might be. we just look at the data and allow it to come out of the data at us, which ones tend to vary together. That's principal component analysis. And then the other one is factor analysis, which is where we do have an idea as to what those underlying factors might be. And and also we're assuming that there is some logical connection between the things that vary together, that there is something tangible lying underneath it, like the fact that they're all sports programs. Whereas with principal component analysis, we just say, oh, well, these programs go together. We don't really know why or care why. So they're really just a kind of a philosophical difference in how you approach it, rather than, well, they may give the same results at the end of the day. You know, you will find that the same sets of programs, you know, swing together in terms of describing people's watching habits, but it's just a different approach, a different you know, philosophical starting point. Now, I'm going to describe the sort of ideas underlying these, but you know, in reality, you're not going to do these calculations from scratch, because they're, you know, very complicated, and you would use some package like R that I mentioned earlier, or WECA, the machine learning environment. WECA, that's a K. You know, so if you were wanting to get into principal component analysis, factor analysis, you would get these applications, and you'd read their documentation and look at some examples to get a feel for what you do and what it's all about. But in this lecture, I'm just going to, you know, bring you up to speed on the basic ideas involved, so that you know what it's about, and because these techniques are used in theoretical history papers, so you want to have heard of it. Okay, so I said we'd start looking at the idea of principal component analysis, and as an illustration of that, I've taken this idea that we've looked at, we've done a survey of various societies, and we've characterized them in terms of their population and their territorial area, A. And we've got these points. And there is a certain amount of variance in the area. You know, it can vary from there to there. And there's a certain amount of variance in the population. Varies up and down there. And to describe where a particular society is, we're going to have to you know, specify the area and the population, because if we just specify the area, the population, you know, can vary quite a bit, and these are, you know, there's no particular law. I mean, we can sort of see a law, but there's no particular law relating them. So if we said that it's that area, the population could be anywhere along there, because we know the population varies along that over that range. But what we could also notice here, that there is this kind of relationship, and we've drawn these axes, population and area, that causes these dots sort of to lie at a diagonal. But we don't need to draw our axes like this. We could imagine these dots as sort of like stars in space, or fireflies in the air, something like that. They are where they are. We could draw our axes any way we like to describe the position of them, to give them some coordinates. We've put them in terms of population and area because those are the sort of intuitive variables that we understand. But we could choose some other variables that perhaps describe them in a different way. And the idea of principal component analysis is that we choose our variables so that we find a first principal component that maximizes the variance. So in this case, in all cases, the total variance is going to be equal to the two variances added together. And in this particular case, we've got quite a large variation in both area and population. But if we choose our variables in a different way, we're going to end up with the same variance, because the variance is what it is. These vary in position. The variance is what it is. But we can choose different coordinate system that makes one of these variances larger than the other. And so that will be the key component. And how we're doing that is, if we get rid of these axes, population and area, we want to choose an axis that maximizes the variance. Well, it's going to be along this direction, because the points vary most in that direction. They don't vary so much perpendicular to it. So that's the direction of maximum variance. So we draw our axes like so, and that's meant to be 90 degrees, and we can call that the principal component 1 axis, and then this is going to be the principal component 2 axis. And now we've got this amount of variation, V1, I'll just write, along the principal component 1, and that amount of variance, V2, along the principal component 2. And we still got, as I said, the same variance, and it's still going to be the sum of the two variances in the two different directions. But now most of the variance is in V1. V2 is relatively small. And so now if I told you just the value of the principal component 1, you would have a much better idea of where that society is in space, as it were, in this space of these two principal components, than if I just told you the area, because there's not much variation. There's not much possibilities in that direction. But locating where it is along here really makes a big difference, whether it's right down here or whether it's up there. And these principal components are defined in terms of the original variables, so or related to them. So we had our original axes, population and area, and like that. So we can say principal component 1 is so much fraction in the area direction and so much fraction in the population dimension. Label these as alpha p is how far along it is in the area direction, alpha a in the area direction, and alpha p in the population direction. So V1 is, sorry, not V1, PC1, principal component 1, is alpha A times the area plus alpha P times the population. And then PC2 will be, and let's say we'll use beta A times the area and beta P times the population. And so that is our principal component number 1, and then there's this lesser principal component number 2. And I've chosen a two-dimensional example because it's something we can see, but in practice we might have many more variables. So these points would be in 3-dimensional, 4-dimensional, 5-dimensional, multi-dimensional space. But we can apply the same principle, that we find a direction in this multi-dimensional space that maximizes the variance. So we kind of rotate the axes to find that, to point it in the direction, the first axis in the direction of maximum variance. And then having established that, we can then rotate still in this multi-dimensional space to point the next axis in the direction of the maximum of the remaining variance. And then that will be 2 lots of variance accounted for. And then we can rotate them again to find the next most direction of the highest amount of variance, and keep going all the way through until we've got down to filled in all the dimensions. We've got a principal component along all the dimensions. So what we'll end up with is a whole set of principal components, and in order of the amount of variance that they explain. And as I say, in reality, you wouldn't do this manually like this. You would just put your data into a statistics application, machine learning application, and ask it to work it out, and it would spit out for you the principal components. So what it would tend to give you these principal components. It would give you the variance that they explain. So that would be a percentage of the total variance, which must add up to 100%. So what fraction of the total variance is explained by each principal component. The coefficients relating it to your original variables. And some metrics of statistical significance. What's the probability of these components having those values by chance? And an example of a piece of work that used principal components is, and that inspires the example I'm using here. Peter Turchin et al. Did a study of social complexity where they identified societies in terms of 9 different variables. Population and area were 2 of them. Another was the number of layers of the administrative hierarchy. Another one was the number of different types of government official that were recognised, and then there were others. So they had these 9 variables, and they took a whole bunch of societies and they characterised them in terms of these variables. So they had a 9-dimensional space, not a 2-dimensional one as we've got here. They had a 9-dimensional space, and they filled all this data, or put all this data into a computer program to do the principal component analysis for them. And they got out then 9 principal components for 9 dimensions. And the first principal component explained 77% of the total variance. And then the second principal component was just 6% of the total variance. And then the third, 4th, 5th were hardly anywhere. A few, 1 or 2% of the total variance each. The whole thing adding up to, as I say, 100%, up to PC9. And so what they concluded from this is that in terms of their variation in complexity, there's really only one underlying factor, this principal component 1. There's not different types of social complexity. Societies are either more complex or less complex. They just vary along this particular direction, and there's a trivial variation on top of that basic variation in complexity. I said societies, there aren't different types of complexity. Well, there is a little bit. The societies can, vary along a different dimension to some extent in terms of, their basic complexity, and then there's maybe some differences, slight differences between this complex society and that complex society. But basically, there's just one dimension, more complex or less complex. That was the conclusion of their study, and that was done with principal component analysis. And the key factor, in fact, the principal component also tended to rely largely on population. So population seemed to be the main explanatory variable. That if population varied, then all these other variables varied in sympathy with it, in correlation with it. So that's the idea behind principal component analysis. As I say, if you want to get more to grips with it, it's a case of getting software that can do it and reading some examples. Okay, and our second approach is factor analysis. And as I said, it's a similar idea. We're trying to reduce the number of variables, and often enough it will come up to similar outcomes. But it's got a different idea underneath it, that we assume that there are some factors that we're trying to find, and we can have a preconceived idea as to what those factors might be. So let's take an example of looking at societies and characterising them in terms of the incidence of war, the extent to which they're involved in wars, the murder rate in the society, the level of rioting, and the amount of terrorism in the society. And so we'll take a lot of societies and we'll score them in terms of where they are on each of these variables, the amount of war, the amount of murder, etc. And what we might suspect is, and this might be what our hypothesis is that we're trying to prove, we might suspect that societies have a different cultural propensity for violence, and that it explains all these things. So that if the society is involved in a lot of war, then the murder rate will also be high, and the riots and terrorism will also be high, because this is a society that has a high propensity for violence. And if it's wars, it's peaceful, it's not involved in wars, then the murder rate will be lower. So that it might be that we're assuming that there's underneath this some factor of propensity for violence. And then what we want to do is try to find the extent to which these reflect that propensity for violence. So we're assuming that propensity for violence is a real thing that societies have, but it's not something we can directly observe. But what we can observe is the number of wars and murders and so on that characterise that society. And we're assuming then we're assuming that these reflect in some way that underlying propensity for violence, and we're wanting to find how they're related to it. So it might be, for example, that it's the murder rate that really captures the propensity for violence, and wars and riots are less important. Now, I'm talking here as though there's just one factor, but typically in factor analysis there'll be, more than one factor. And in this case, we might find that when we look at our societies, that yes, although wars, murder, and riots tend to swing together, so that more warlike societies are also more murderous and more riotous, terrorism is different. Some warlike societies have low terrorism, and some warlike societies have high terrorism. So it seems to, it's not swinging with the others. It's not correlated with them. So there may be some other factor, and so we might hypothesize that, say, political openness, say, is another factor. So societies are described by these two things: propensity for violence and political openness. And those are the two factors underlying their scores on these 4 variables. And how we then approach that is that if we take our variables, we're saying that war, which I'll represent with a W, is equal to some factor. I'll put alpha 1, 1 times the propensity for violence, which I'll represent with a V, plus some other factor, alpha 1, 2 times political openness. So our factors of violence and openness affect wars, or related to wars, by these 2 coefficients, alpha 1, 1 and alpha 1, 2. And the same for the other variables. Okay, so I filled in for the other variables these equations, relating them to our underlying factors. So the murder rate depends on violence and openness. The amount of rioting depends on violence and openness, and the amount of terrorism depends on violence and openness by these coefficients. And we want to try and find out what these coefficients are, how these variables, the things that we can observe, are related to our underlying factors that we can't directly observe. And we might find, for example, that for terrorism, this coefficient is quite large. In other words, terrorism, the incidence of terrorism depends quite a lot on the political openness, but it's less affected by this violence factor. For something like war, we might find that it depends largely on V, and alpha 1, 2 is less relevant. Political openness doesn't really affect the propensity for war. With something like rioting, we might find that it depends on both. It's partly dependent on political violence and it's partly dependent on openness. Both are important. So we'll get different values for these coefficients. And what we have to do then is take all our societies where we've got values for W, M, R and T for each society, and we then try to fit it to these equations and see if we can extract these factors. And we're going to find the best fit. What are the values of these coefficients and the variables at V and O for each society that best explain the variation we see in those 4 variables W, M, R and T. In this case, I've written it as though we're looking at the how the war depends on V and O, but actually what we really want to find is normally the other way around. We want to work out our factors of propensity for violence for each society, for example. We want to know how they depend on the things we can observe. So this set of equations gives W as a function of V and O, let's say, and also W, M, R and T as functions of V and O. But what we would really want is V as a function of W, M, R and T, and O as some function of W, M, R and T. So that's just a case of rearranging these equations to make V and O the subject of the equations in terms of W, M, R and T. So yeah, we just do it the other way around, and then that's what we will ultimately interested in finding, the coefficients that should go in front of W, M, R and T to describe V and O. So let me just perhaps double clarify that. So we'll have something like V equals, let's just use beta, so it would be beta 1 1 of W plus beta 1 2 of M plus beta 1 3 of R plus beta 1 4 of T. And then there will be one for O, which will be beta 2 1 of W, beta 2 2 of M, beta 2 3 of R, and so on. So all I'm saying is that what we're really interested in is finding these betas. And again, that's just the principle. You wouldn't write out these equations and try and solve them and rearrange the equations to make V the subject to the formula. That would all be done for you by a computer program. You would use a computer program for factor analysis, and you would feed in what your data and get it to do all the work for you. Now I said here that we kind of can assume in advance what factors we're looking for, and if we do that, we might also predetermine some of the coefficients. For example, we might write in our formulas, we might say, well, actually we don't think that terrorism is going to depend on violence, so we'll just do it like that. We're not going to look for a coefficient. So you can predetermine in your system of equations here something about how you think these variables are related to your underlying factors, if you want, and sort of force the system to support your way of thinking about it. As I say, that's just like an option if you want to do that in your approach to factor analysis. But going the other way, you can do factor analysis where you don't make any assumptions about what your factors are, so-called exploratory factor analysis, so that in that case you allow the factors to emerge naturally. You don't assume how many there are, and that is basically the same as principal component analysis. So exploratory factor analysis is is another name in effect for principal component analysis, though it might be done in a slightly different sort of the detail mechanics of it might involve a slightly different approach. Okay, so with the principal component analysis or factor analysis, we find these underlying components or factors, and we're saying that those explain the variations in the observable variables. But how accurate is that? Is that just caused by chance, or are these real factors that we've identified? So for example, in the Turchin study, they found that there is this principal component that explains almost all complexity. But was that just an artifact of that data set? Or is that a real thing that we can say genuinely applies to societies throughout history? Well, how can we tell? Well, one way to tell is to take our principal components that we've found with this particular set of data, and then go to some fresh set of societies, some new set of data, and see if those explain the variation in the new data. And if they do, then we can say then these are real, because they apply to fresh situations. They aren't just the ones that just work for this particular data set. They seem to work generally. What you then want to do is normally you're not going to have a lot of data and then go out and collect a lot more. You just collected a lot of data on societies, so what you can do is just take, say, half the data and use that to work out the principal components, and we call that the training data to find the principal components, and then you go to the other half of the data which you've kind of kept in reserve, and you test it. You test your principal components on this other data set. So that's the testing data. But the problem with that is it's kind of wasteful of data, because you you really want to get the best, most accurate view of the principal components. It would be nice to use lots of data, not just half of it. You want to use the whole of it. But then if you use the whole of it, you've got nothing to test it on. So there is a technique, cross-validation. Well, so in fact really a whole set of techniques to allow you to test your discovered components or factors on the data, while not sort of wasting it, but being able to use it for both training and testing. And the basic, I'm just going to show the basic idea of that. So if we imagine the data as sort of in a box, this doesn't really mean anything. It's not really sitting around in 2 dimensions, but it's just to illustrate the idea of how we divide it up. Oops. So there's all this data. We can firstly divide it into a few subsets, and we train on each subset. So we do a principal component analysis on that subset, in this case a third of the data, and on that a third of the data, and on that third of the data. And what we're looking for is to see if we get the same basic principal components out of it. If we do, that's a good test to start with, that our principal components are meaningful, because all these different subsets of the data are giving the same value, and we haven't wasted anything. We've used it all. But then we can also further validate what we're doing by testing the data on another way of dividing it up. So having trained it on that third of the data, we can then test it on this third of the data. So that's a different subset of the data. And then we do the same here and the same here. And that is known as cross-validation. It's a way of once you've got your principal getting principal components, but also testing them in a new environment and seeing if they still hold up, because that's a way to build your confidence in them, to get a feel for whether these are just chance results or whether they are statistically significant. And once more, you wouldn't necessarily think about doing this sort of manually. Your machine learning program, statistics program would have these cross-validation techniques built in, and you would select the one that you wanted to apply. Because this is just an abstract way of describing it. There are, as I said, many different ways of doing cross-validation.